Cool. Yeah, thank you. I'd like to thank the conference organizers for the opportunity to talk, and I'm really excited to present some of the cool research that we've been working on. Okay, so I'm going to give you a bit of a motivation, like why we're interested in working with drones and cars and other mobile platforms. I'm going to give you kind of a brief overview of our system, show you some results, and then tell you what we're thinking of for next steps. Okay, so let's start with the motivation. So the prior panel was discussing the possible notions of the future global internet. So fundamentally, a global internet that is quantum could give us secure communication, distributed computing, as well as distributed sensing networks. And so if you really think about it, those are potentially large benefits. And if that's the case, it may be worthwhile to extend those benefits for on-the-go applications, such as cars and planes, ships, as well as drones. So prior quantum key distribution links have been demonstrated for satellite to ground, ground to airplane, airplane to ground, drone to ground, and stationary to moving vehicles. So this is kind of like our vision for what we imagine that the future quantum network would be. So obviously, you have to have fibers, and then there are a lot of people that are studying satellite to ground links. In fact, there's multiple talks on that later today. But we also really see the idea of using like drones, vehicles, and having that interconnect to other planes. So our work really focuses in this middle region, where we're going to be studying drone to drone, drone to car, and car to car QKD links. Okay, so let me tell you a bit about our system. So in order to do this, you need a QKD source. You need a way to prepare the quantum states. You need a way to transmit those quantum states from one moving platform to another moving platform. So you'll need a pointing, acquisition, and tracking system. Additionally, you'll need a way to measure the single photons, project them, and then to measure them using single photon detectors. You'll need a time tagger and a way to synchronize the links. This is a nice picture of our drone, our QKD system before it takes off. This right here is our beacon laser, and I'll discuss more about that in a second. So, okay, so what is our general approach? So we really wanted to do a modular design. We started off by trying to have our source very highly integrated inside our platform, and that turns out that you don't want to do that for a lot of reasons. It's much more convenient, it's easier, and it's a lot more scalable in the future if you have this modular QKD transmitter, a modular QKD receiver that can just be connected to a drone, to a plane, or to a vehicle. So to do that, this is what our system looks like. So this is our transmitter, Alice, our receiver, Bob, and this is what it looks like in an inverted configuration. We have the ability to connect it on the bottom of a drone. So we've got a gimbal. This is some of our pointing and tracking sensors here. We have this broad equipment tray that all of our custom hardware goes, the QKD source, the single photon detectors, et cetera. And the real takeaway here is that we do not share any power, control, or communication with the host platform. And that allows for much easier integration into the platform. Okay, so that's a bit about kind of like the high level view, and let's talk about our QKD source. So our QKD source, we partnered with The Ohio State University and our collaborators, Roddy and Daniel, which are actually over there. They presented some really nice posters earlier in the week. They took the lead on this. So we're using a decoy state QKD. We use a signal with 2 decoy intensities, and we're choosing to use the right and left circular bases for our signal states, and our air checking is in H. And the reason we did that is that if you've got the drones and there's any sort of relative rotation with respect to each other, the right and left circular will not induce bit errors during the transmission, because it's just detecting whether you're rotating to the right or to the left. And so we use 3 different resonant cavity LEDs, and the reason for this is we want very good spectral overlap. See, one issue with using lasers is that if you have 3 different lasers, you'll most likely have 3 different wavelengths. Whereas for LEDs, we can put them through a common 1 nanometer narrowband filter, and we get a really nice spectral overlap that is on top of each other for our signal and our decoy states. Additionally, we took a great deal of care when analyzing side channel attacks. So we have good spectral overlap as well as we have good temporal overlap. Here's a temporal view of all of our signals. And we put them all through a common single mode fiber so that they are in the same spatial mode. So once you have a QKD source, you need to prepare the polarization states, and then you need to transmit the polarization states from one drone to another drone. And it turns out that's a really hard problem to do. You have to contend with relative drift, vibrations, and motions of the drone platform. So to do that, we require a pointing acquisition and tracking system. And we have that in two different parts. We have a coarse adjustment, which is listed here, and a fine adjustment, which I'll talk about next. But our coarse adjustment consists of a gimbal with an IR beacon and an IR camera. So it essentially looks off into space, sees where the other drone is located, and that generates an air signal to rotate the gimbal so that they're both looking at each other. So typically, once we get the drones in the air, they start the acquisition phase. As soon as they acquire the target, then it takes about a second in order for them to track on, and then this is while they're tracked on in the air. So some of our in-flight performance, our RMS air for pan is around 0.023 degrees, and for tilt around 0.026. And we're very happy with those results because that's pushing very close to what the actual jitter specification is for our gimbal, which is around 0.02 degrees. So this is good, this gets you in the ballpark, but it turns out you actually need another tracking system to get better performance. So this is our fine adjustment. Our fine adjustment uses two counter-propagating laser beams and fast steering mirrors. So kind of what's going on here is we've got a QKD source on our transmitter. It goes through the stack and is detected here by our receiver. And we've got a 705 beacon, which propagates through the free space channel, and that is detected here with a position-sensitive detector. Additionally, we have a 520 nanometer beacon, which is back propagating through, and it's detected here. And based on the position of the beam on the position-sensitive detector, that generates a local air signal that feeds back to control our fast steering mirrors. And some of our tracking performance, this is on the table, like on the benchtop, we're able to get pointing errors RMS of around 21, 22 microradians. And when we get it in the air, we're not able to keep that good, but some of our best air-to-air tracking performance is hovering around 40 microradians. Okay, so it's kind of like a bit of an overview of our system. And let me talk about a bit of our results. So our general paradigm is we first establish the link classically, and then we deploy our QKD source. So here's a picture of our drones in flight. So we're using the Alta 8 Pro drones. They have about a 20-pound payload capacity. And so that's very challenging. All of our system has to fit within 20 pounds on the transmitter. All of our system has to fit within 20 pounds on the receiver. Additionally, we are only able to stay in the air for anywhere between 3 to 5 minutes, depending on weather conditions and exactly what the weight of our particular test flight is. But what our typical sequence is we start on the ground, we take off, we acquire the other drone, and when both drones are locked on, we get a channel loss in dB of around minus 2.25. which corresponds to approximately a 60% transmission. And this was done when the drones were approximately around 10 meters apart in the air. So we did it classically, and then we moved to doing it with our QKD source. And here's a little video clip of our drones in action.
This is air-to-air QKD flight number 3, November 1st, 2022.
So, yep, they're just hanging out, hovering, exchanging the QKD key. And this is what some of our performance is. We did 3 particular flights, and we measured an average Q of around 2.9% in the right and left basis and around 3% in the air checking basis. And we are collaborating with the Waterloo group, the Lukenhaus group, and Scott and Lars are our collaborators, and they're also here today, and they presented really nice posters earlier in the week. So that was our drone-to-drone QKD results. So now I'm going to talk about our drone-to-car. So what we did for this is we had the transmitter in the drone right here, and we had the receiver on the car right here. And we had the drone and the car traveling parallel to each other down the road. And when we do that classically, we can get around a 38% coupling efficiency into multi-mode fiber. And our QKD performance, which is located here, we were able to get around 6.4% QBER in the right and left basis, around 3% in our air checking. And we started off with the drone in the car stationary, so we were getting very nice transmission. But then while they're in motion, they're contending with the disturbances, and so our signal drops a bit. You can see the counts go down, but we're still able to get signal, and we're still able to time sync on those and actually get QBER through the channel. So that was drone to car. Now I'm going to talk a bit about car to car. If we can put one of our payloads in a car, we can put the other one in the car, and this is essentially what our setup is. So we have the transmitter in the backseat of one vehicle, our receiver in the backseat of another vehicle, and for this particular test, we had both cars traveling down a country road in Illinois, and we measured classical coupling efficiency as a function of time. So you can see when the cars are stationary, we get really great coupling efficiency, around 80%. When the cars are in motion, the road we did this on had a lot of potholes, a lot of bumps. And so you can see this, we lost signal at times, but then our pointing acquisition and tracking system reacquired. And even with the dropouts, we're still able to get around a 55% coupling efficiency through the channel. So, this was slow speed on a country road, but really, we're interested more in like going faster and pushing it further and, trying to get it on the highway. So this was a bit of an aggressive test because we wanted to do a 70-mile-an-hour vehicle-to-vehicle quantum transmission. So if you're not familiar, Illinois is in the middle of the United States. This is our state, and Urbana, Champaign is located right here. So we literally got on the highway, had both cars traveling 70 miles an hour in cruise control, so they were right next to each other. We had a quantum transmission between one car and the other car, and then we broke off and then turned around and then repeated it going back. So I mentioned that we had a laser for our fine pointing acquisition and tracking system, and so this was a public highway. We did not close it off, so we actually had to turn off the laser for obvious safety reasons. So this is just with our near IR beacon, which is outside of the spectral range. It's around 850 nanometers, and just with our gimbal, our outer control loop. So in a certain sense, the system had like one hand tied behind its back in order to do this test, but we just wanted to see where we're at. So here's a brief video of both vehicles traveling 70 miles an hour in cruise control, performing a quantum transmission. So this bright spot right here is the near IR beacon on the receiver. This right here is the gimbal of our transmitter. So the signal is literally going from here to there. Now, when you look at this with your eyes, you're not able to actually see this beacon with your eyes because it's outside of our range, but the camera was able to pick it up. So we also had to roll the windows down because we found that the tint on the window was messing with essentially our signal. So this was done, that was done in December, so it was a little cold for the grad students. So this is some of the performance that we measured. So we used both a multi-mode fiber as well as a single mode fiber on the receiver. And when we go into multi-mode fiber, we get a really nice signal to noise ratio of around 28.6 dB. So this is our signal, and this is our background. You can see we get really great coupling with no dropouts. That probably is because the highway is very smooth, and it was performing well. When we go to single mode fiber, that's obviously much harder because the mode field diameter is significantly smaller for single mode fiber. But even though we were only using one of our control loops, we're still able to get an average signal to noise ratio of around 17.4 dB. And the reason our advisor was really pushing us to do single mode is that single mode is required if you want to do quantum teleportation, entanglement swapping, etc. Okay, so let's do a bit of a summary. So in summary, we presented on a drone-to-drone QKD link with a QBER of around 2.9% in our right and left basis and around 3% in our air checking. That corresponds, and we measured around 60% transmission. And we believe this is the first demonstration of a drone-to-drone QKD link that's been reported on. Additionally, we discussed our drone-to-car QKD performance. The QBER was a little bit higher. We're still able to get around 30% mean coupling efficiency. And again, we believe this is the first demonstration of a drone-to-car QKD link. And finally, we presented a car-to-car quantum link traveling 70 miles an hour on the highway, and we achieved these signal-to-noise ratios. And again, we believe this is the first quantum network established on a US highway, or any highway thereof. So, okay, so what are our next steps? Well, we have a few system upgrades we'd like to make to our system. At the moment, you've probably noticed all of our testing is done at night. That's just to keep the background down and have our tracking system work better. So in order to go to daytime operations, we need to couple it more into single mode fiber, as well as to add some additional spectral filtering and potentially use pulse beacons. So we can essentially pick out our beacon as opposed to any other reflections from the sun. Additionally, we'd really like to go to longer distances. Some of our tracking system works really well. This is the near IR beacon as seen by the gimbal at a distance of 275 meters. So that was really good. So we're trying to go to longer distances. Additionally, we'd like to also perform entanglement distribution. Professor Kwiat has another project in our lab that is sending an entanglement source to the International Space Station. It's called the SEEK project. It's fairly compact, 20 by 30 by 10 centimeters. And we have a copy of this, and we're performing testing right now, and we're going to be deploying that on our drone. So we plan to repeat this drone to drone, drone to car to car with entanglement distribution. And kind of one of the nice things about if you can have a QKD link between mobile platforms such as drones and cars, that is a critical enabling technology that would allow you to do other more advanced quantum protocols, such as quantum position verification. And so if you're not familiar with that, that's a really, I would encourage you to check it out. We expect that would be very important as we are migrating towards this fully autonomous self-driving car smart infrastructure. It's very important that we make sure that if everyone's in a self-driving car, that those communication links are secure, that the vehicles can know where they're located, as well as just providing, we expect quantum QKD as well as quantum position verification to be important for our future smart grid. I'd like to thank our research team, our Professor Paul Kwiat, as well as our co-PI, Professor Dan Gauthier at OOSU, as well as the research team, Samantha, Timur, Roddy, Daniel, myself, and Shuin, as well as we'd like to thank our funding sponsors. And I'll open it up to any questions.
Thanks for the nice talk. I have two questions. One is how to generate the signal and decoy state in your QKD transmitter. And the second question is how to compensate polarization between two remote objects.
Very, very great questions. Okay, so I have that as a backup slide. So I'll answer your second one first. So this is a picture of our of our actual optics setup. So we've got right, left, and H that go through. This is our spatial mode fiber here. But in order to compensate, we have a stack of polarization compensation here, consisting of quarter wave plate, half wave plate, quarter wave plate. And then to answer your first question, go back to the source. There we go. So we have inline fiber attenuators that we attenuate down so that we can do power balancing between the states. And then on this board right here is a custom PCB, and we have resistors that step down the voltage of the driver so that to produce the decoy state. And then one of our decoy states is a vacuum, so we just don't transmit during that time.
Hi, so I had a question probably about the drone-to-drone transmission and I guess the error rates that you observed. So I guess you showed that the RNL basis, has lower, I guess, QBER overall compared to the H and V. Is that because basically you have the two drones which are stationary, so they just basically roll with respect to each other, and so the H and V basically gets misalignment issues, whereas RNL you were saying is essentially better suited because it's more, I guess, resistant to it. And I guess, and then the second question would be, well, if you then have the drone, one of the drones actually moving, would you kind of eliminate that problem where the drones are hovering and rolling?
Yeah, that's a good question. So yeah, so we observed a slightly lower quantum bit error rate for the right and left basis, as you observed. And in principle, yes, while the drones are in flight, there are some rotations, minuscule rotations, and the right and left circular basis by design, or we chose that by design to be immune to that. Yeah, and yeah.
Hi, thank you for the talk. I was wondering if you could elaborate on, so you said like you could be using it as an application towards position verification, but in the threat model for the position verification, it's usually it's not the car trying to locate itself as the adversary, but kind of the threat model is inversed, right? You're kind of swapping the provers and the verifiers, I feel.
Yeah, of course. Yeah, so I kind of glossed over that. The talk isn't geared particularly for quantum position verification, but yeah, in order to do the protocol, the prover in this case, so QPV works by the prover, it thinks it knows its location, and it's trying to prove, hey, I'm really here to other verifiers. So yeah, I agree. You can't use QPV as kind of like a GPS. If you're trying, you have to know where you're located, and you're trying to prove where you're located to someone else. So yeah, so this talk is primarily about QKD, but the point is the link that we've established between mobile platforms could be leveraged to also do quantum position verification. So yeah, you have to think a bit more about what the applications are of interest, but it could be that a car is trying to prove like, hey, in fact, I was here at this location when an accident occurred, as opposed to this other location. And I have the logs and the data to show that. So yeah, that's a good question.
Hi, thank you for the talk.
Okay.
Can you say anything about how your system performs when you have motion that's not basically stationary between the two platforms, or parallel motion, where one is stationary and a target is moving?
Yeah. So that's a really good question, and that's something that. So yeah, all of the research that I presented here is with either the drone stationary or the drone and the car moving in parallel with each other, so at a fixed separation distance, or two cars moving parallel to each other, again at a fixed separation distance. So in order to, so our advisor is pushing us to do more of the configurations that you just mentioned, Matthew, where essentially you've got one car that's moving relative to another, or you've got a car and then the drone is moving, and then moving away from it. In order to do that, we need piezo mirrors or piezo focusing lenses, so we can essentially like adaptively expand and compress both our beacons as well as the quantum beam in order to maximize coupling efficiency. Let me see if I can go. Yeah, so this is an older photo, so we don't have it, but essentially right here on our transmitter, we've since upgraded that to have it's called the M3FS, but it is a piezo focusing lens, and this is our beacon that's being propagated out. Again, that has since been upgraded to a piezo focusing lens. So we have the hardware in place. We just need to do more of the testing and update the control system to adaptively figure out the distance between the two, as well as to expand and contract the beam diameter appropriately. So we have the hardware in place, but we haven't done the testing yet to realize that. But that's on our to-do list.
Yeah. Thank you so much for a great talk, and thank you for sharing with us. And I have two questions. One question is the QBR calculation and key shifting is done real time? And the second question is, you're putting everything on a drone, then I think drone will be suffer a lot of vibration. Do you need extra damper to compensate it, or is just using the fast steering mirror is enough for that?
Yeah, so that's a really good question. So as far as calculating the QBR, I'll go back a sec. Yeah, so as far as calculating the QBR and doing the time synchronization, at the moment that's done right now in post-processing. And as far as the vibrations, the vibrations are like one of the worst parts of this. I kind of envy the people doing satellite to ground, because the satellite is like, very smooth and is not vibrating. So the short answer is you need both. So we have two control systems. We have this outer control loop, which uses a gimbal, as well as the inner control loop. But the drone itself has mechanical vibrations isolation between the motors themselves and this gimbal platform. So we have mechanical isolations, but then we also have the coarse tracking, which is done with the gimbal, and then the fine tracking with the fast steering mirrors. We put accelerometers on the drone, and we measured some vibrations in excess of 850 hertz. So we essentially are pushing the fast steering mirrors as fast as we possibly can to get above those disturbances. So to answer your question, you want to do as much as you can with mechanical isolations to help you out. In addition, that you need to have a high control bandwidth for both fine and coarse tracking.
Okay, well, let's thank Andrew again.